Hi everyone, my name is Girish Baliga and I'm Director of Engineering at Uber. Today I'd like to share how we have built Uber's data infrastructure using open source technologies and how we have customized it for Uber's unique business use cases, making it reliable, scalable, performant, and multi-cloud. Uber's mission is to help people go anywhere and get anything. And we're doing it at over 10,000 cities all across the world today. We have about 137 million monthly users. These are the latest numbers. And we are covering over 25 million trips per day. So as you can see, the scale is huge, it's global, and that means we have really complex and large scale problems to solve for data infrastructure to power the insights for all of these Uber use cases. So let's jump in and see who are our different customers. So our biggest customers are our community operations teams. These are the teams that run Uber businesses in all of the 10,000 cities that I shared. They're responsible for running the business, working with local authorities, uh, getting insights, providing reports, and overall making sure that our business runs smoothly. Then we have our marketplace team, which runs the Uber marketplace for all of our different businesses, including rides, eats, freight, and so forth. And then we have our eats teams, which are building the engineering and operations for our eats offerings and our groceries and new articles. And then we have compliance. We have growth marketing, which is a big team that works on getting insights on how our businesses are running and how we can customize our businesses and drive incentives to grow the business. And finally, data science. So these are machine learning and data science engineers who are essentially diving deep into our data and getting insights on how to improve our matching algorithms, our connections, and our overall end-to-end system. All right. So what are all these users looking for? They are trying to go from our data to insights. So what is an insight? An insight, simply defined, is an answer to a business problem based on relevant data. So here's an example of a business problem that we face at Uber. What are the interesting orders near a given location? So to answer this question, we have data, which is a table of all the orders that we have had so far. And then we run it through this box that we can call analytics. And then we get some insight, which basically might look something like this. All the trips or all the orders near a location like San Francisco. So if you were to do this as a programmer, you would start with a data set of orders, and then you would write a program which looks something like this. You would load your data set into an in-memory data structure using your favorite language, Java, C++, Go. And then you would write some algorithms, or maybe even use out-of-the-box algorithms to operate on these data structures. And finally, you would write some business logic that would leverage these algorithms and data structures to answer the questions you really want. Like in this case, what are interesting orders? So this is all fairly straightforward and pretty easy to do. But the challenge comes when you're trying to scale this up. So the first approach that most people try to scale this is to take their program that runs on a single machine and try to make it run on a host of machines. So it turns out that this kind of architecture where you're taking a simple node and replicating it turns out to be a very, very hard problem. There are lots of challenges in getting the data spread across the machines, making it consistent, building distributed algorithms, and making sure your logic is able to use all of these things effectively. This was probably the state of the art 60 years ago. And then we had about 2 to 3 decades of computer science. And we finally ended up with a design like this, where you would write a program that would leverage a distributed data system, right? Maybe a key value store to store all your data, and potentially a cache to make sure that your algorithms run fast. Essentially, you're shipping the problem of data scale out, but then you're still uh, building distributed algorithms that is using this data from your distributed data store. Another decade or so of evolution later, we end up with our current system architecture, where you basically use an analytics engine. So an analytics engine is able to not only handle the data scale, but also is able to operate on this with distributed algorithms. And then you're just left interacting with this engine using a high-level language like SQL. So with this kind of architecture, all you do is you focus on the SQL that you need to solve your problem, and the engine does the rest. So let's see how we can answer our question using this third model of analytics. Again, to restate the question, what are the interesting orders near a given location? So if you were to answer this question using SQL, you would just have 4 lines of code like this. Let's say select star from orders where the distance from a point in the order is within a certain radius. That's it, 4 lines, and you have the answers that you need. But does this really work for all our users at Uber? Let's take a look. All right, so first off, we have a class of applications which want to know the orders by area in real time, right? So they are operating in a regime where they need data freshness in under a minute. They want to be able to compute this in multiple areas all at once. And they want to integrate with a real-time system like, let's say, a Kafka topic. So this branch of analytics is called streaming analytics. And this is used to compute real-time problems at Uber, things like surge or marketplace imbalance, where we need to change our pricing algorithms. A second class of problems looks somewhat like this. What are orders near me right now? So if you are using the Uber Eats app, for instance, in the feed page, we show what are popular orders in your area. So we are answering this question pretty much for every single user every time they open the feed page. Here we are looking at slightly lower data freshness, let's say 15 minutes, but then your scale is much bigger. You're handling traffic on the order of 2000 queries per second. And your integration is typically an RPC interface because you have a backend system for your feed, which is querying an engine. Then we have a use case where we want to show orders, a summary report for, let's say, a restaurant manager, and summarize what were the orders and how the business did for them today. Here, the data freshness is about a day. Scale is probably multiple reports per restaurant owner. You can probably run this every few hours or once a day. And you have some sort of an integration where you have like a query runner or an orchestrator that can run this query on a scheduled basis and give you the insights. And finally, we have batch analytics, where we're trying to understand what are order trends in the last year. So here we're looking at historical data, right? The last, let's say, year plus of data. And you would integrate this with some sort of an interactive interface like a query builder, and you would probably build some automation on top. So some of these are Uber technologies, which I'll get into later. But at a high level, you can see that there are 4 big boxes of analytics that we need to power for our users at Uber today. All right, so let's look at how we do this. So we have a stream of data coming in, like the orders in our example. And then from this, we need to generate signals, compute search, for instance, marketplace imbalance. We want to power insights for our users in our Uber Eats type products, like the Uber Eats feed. We want to build daily, weekly, monthly reports. So these are, for instance, the restaurant insights. We want to do analysis, so figure out order trends. And then we want to build machine learning models that can improve our algorithms in our serving systems. So to power this, we use the standard architecture in the analytics space called the Lambda architecture. So we have streaming analytics, which sucks in the data in real time, lands it in a real-time data store, and then this is available through a query interface for the products, for the signals, and so forth. So this is how we do real-time data serving with low latency, right? High freshness data. And then for the batch use cases, we take in the same data, but then we ingest it into a data lake. And then we run some analytics on top of it, some transforms. We create data models, and then we provide another query interface on top of these data models for users to build reports, do analysis, and power machine learning. Okay, at Uber, we can put some names to these technologies. Our data stream is Apache Kafka. Our analytics is powered by Flink. Real-time data is served on Pinot. And on top of Pinot, we have built a custom Presto query interface so that our users can write Presto queries, Presto SQL, and run their queries on Pinot in real time as if it were a production backend system. On the batch side, we run our ingestion jobs on Spark. We have built a data lake using open source technologies, Apache Hudi, which is something we built at Uber and contributed. We use Parquet as a file format and Hadoop as a storage layer. And then we have Hive jobs, which we then take to ingest data from the data lake and build a data model using pretty much the same stack. So we have Hudi as a table format, Parquet for files, and Hadoop to serve all the data. And finally, the engine that powers interactive queries on top of a data lake and data model is Presto. So as you can see, we have built our entire infrastructure for data analysis at Uber using open source technologies. And we started off with about 10 or so technologies 5 years ago. And we have been able to boil it down into these 4 key analytics engines, as I shared in my previous slide. All right, so let's see how this works in practice. So we have a common SQL format that our users can use. So they use Query Builder, which is a tool I referred to earlier. So this is, you can think of it as a SQL editor that our users use to build a SQL query. And then they interact with our Presto system to refine this query. So this is the equivalent of if you are writing code in an IDE, you would work to develop it on your local machine. And then once you're happy with your SQL, you can push it to production. And our production interface is a tool called uwork. So this is an interface that can take in a Presto SQL and then push it to production. So what does that mean for the 4 engines I referred to? So we are able to take a Presto SQL query and build a Flink job out of it, right? This is able to take a SQL and run a transform in streaming fashion. So you're constantly computing signals needed for various use cases. You can take the same Presto SQL query and run it in real time. So at the 2000 QPS scale I referred to earlier on top of Pinot to power product features. And you can also run the query on top of our data lake to build interactive reports or to run massive Spark jobs to power machine learning use cases. As you can see, this is what SQL provides, right? If you have a declarative language, then you can decouple it from your implementation. And under the hood, you can convert it using a variety of engines to serve pretty much every single use case you have for your data infrastructure in your company. All right, so our main query language or a default query language is Presto SQL, as I shared. So this is our default solution for our analytics, and it addresses the majority of our use cases. But this is not enough because we have users who want to customize the SQL, right? They want to have some custom UDFs, or they want to tune the resources because their queries are really big. There are also our data engineering users who want to build ETL jobs to model our tables or to run scheduled analytics. So for these kind of users, we have customized Flink SQL or Spark SQL, which are flavors of SQL for the corresponding engines. And for advanced users, we also support programmatic APIs, but with Uber flavor. So we have Uber approved Flink libraries and Spark libraries that our users can use to build low-level API-based programs using languages like Java, Scala, Python, and so forth. Flink in particular addresses offline needs for real-time use cases like search, metrics, ETA computations, and so forth. And Spark addresses offline only use cases like ingestion, ETLs, ML training, and so on. So we do support a variety of query languages, but if I were to talk about the number of users, Presto is probably in the thousands, Flink, Spark in the hundreds, and then the APIs is probably in the tens. All right, so now we've seen how we've built our infrastructure using open source technologies and offering a variety of SQL languages with a common default. But how do we do this reliably? All right, let's take a look at one subset of our stack. So here we have HDFS, which stores the data, and we have Presto, which can be used to read and write that data. And we have routers, which are providing an abstraction between these two. So first, for our data, we build reliability and scalability by storing multiple copies, right? So we have multiple copies. So in case one copy is corrupted, we have two more. And if there are hot shards, we can add more replicas so that we can handle the read traffic. We also use erasure coding and tiered storage for older data so that we have a much more efficient way to do this at scale. And for our table format, Hudi, from Uber, we have contributed record index, which is an advanced way to build a transactional layer on top of Hudi, which does not use a side key value store like HBase. So this format allows us to build a transactional layer extremely scalably on top of HDFS. Similarly, with Presto, we run multiple clusters, and so we use these clusters to do tiered compute. So we have separate clusters for interactive versus offline scheduled queries. We also do smart routing of queries so that the heavy queries we put in different clusters from light queries. And in case of errors, say there's a cluster deployment or a restart, we are able to do automatic retries. And if we have a regional failure, we also have a provision for a secondary region. So we basically copy data from our primary to secondary region using HiveSync. And this allows us to do multi-region deployment so that in case of a regional failure, we have a standby Presto cluster where we can move over some high tier jobs that need to run right away, and then with a degraded SLA for other tiers of jobs. All right, let's take a quick look at performance. So digging a little deeper into Presto, a Presto cluster looks like this. We have a coordinator and a bunch of workers. Similarly, HDFS cluster has a name node and a bunch of data nodes with the data residing on HDDs. So one of the first optimizations we did in the stack is our Hudi listing optimization. So we are able to be smart about the way we do listing on Hudi, and we've optimized Presto to do this, customized it for Hudi. And similarly, the actual data reads, we have done a bunch of optimizations within Presto. So we've implemented a vectorized reader, and we have done nested column and predicate pushdowns to significantly reduce the speed at which Presto is able to process data. We've also integrated a Luxio library within Presto workers so that we can use the local SSD to cache data. So these are high access data, so sort of dim tables that are used commonly high value fact tables, in some cases, the most recent partitions. And we use affinity scheduling to make sure that the cache is properly exploited. Similarly, on storage side, we use Luxio local SSDs to cache for faster I/O. As you can see, with a single SSD, we are able to replicate and keep a copy of all the hot data so that all the reads run very fast. So these are some of the contributions that we also made back to open source about how you can run your stack in a performant fashion. Finally, for multi-cloud, we have traditionally had on-prem deployments of our stack. Here you can see again our standard Presto stack with HDFS and a high meta store with the table metadata. So for our data cloud, we are currently building it out on Google Cloud. Here again, we're using HiveSync to copy data from HDFS to Google Cloud Object Storage. But interestingly, we are directly using the object storage without HDFS in the middle. And we've actually been pretty impressed with the performance we're getting here. We are directly using Presto on top of object storage, but we are using a HDFS client. So we've built a client on top, customized the HDFS client so that it can use the Google Cloud storage directly, while Presto still thinks it's querying HDFS. Similarly, there's a meta store in the cloud for the tables which have been subset of the tables which have been replicated. So whenever there's a query coming in, we have updated our Presto router to do query analysis using the Presto SQL stack. Again, something you can do because Presto is open source. So we do a query analysis. We get table information, what tables are being queried, what tables are being written to. And then we can query the HMS to see where these set of tables are available. So if they're available on-prem, we can run the query on-prem. If they're available on the cloud, we can run it on cloud. And we can also use this information to do smart placement of data across on-prem and cloud. So then the router takes all of this information and then is able to route smartly based on the table usage information and the availability in on-prem versus cloud. So hope you all enjoyed that short trip through Uber infrastructure, and you were able to see how we are able to leverage open source technologies and build an entire stack at Uber scale, addressing all our requirements, all using open source. If you'd like to learn more about any of these engines or any of the topics I talked about, please head on over to our engineering blog. We have written multiple excellent blog posts covering a lot of these things in detail. And if you'd like to reach out to me, here's my email and LinkedIn. Thank you all for attending my talk and hope you enjoy the rest of your day and all the other talks at Open Source Data Summit. Bye.